Let's derive the Euler's formula. The Euler's formula is given by ej theta is equals to cos theta plus j sine theta. The approach to derive the Euler's formula is this. We use Taylor expansion to represent ej theta, as well as cos theta and j sine theta. And then we'll see that the left hand side of the Taylor's expansion equals to the right hand side. What is the Taylor expansion or the Taylor series for these three expressions? Without a proof, we'll just state the results of sine x. So sine x is an infinite series where sine x is, when represented as the Taylor expansion, is x, so whatever x is here, minus x to the power of 3 divided by 3 factorial plus x to the power of 5 divided by 5 factorial, and so on. Cosine x is this expression over here. So it is actually 1, but you can think of it as x0, because x to the power or x to the exponent of 0 is 1, minus x to the exponent of 2 divided by 2 factorial plus x exponent of 4 to the exponent of 4 divided by 4 factorial. So you see that the cosine has even terms of the function of polynomials, while sine has odd terms. And this is reassuring because cosine is an even function and sine is an odd function. Now when you perform the Taylor expansion of ex, so this should be known to you. The short form notation of e to the exponent of x is this: x to the exponent of k divided by k factorial, sum it to infinity. So when k equals to 0, then we have 1. When k equals to 1 is x divided by 1 factorial, which is 1. Then x k, where k is 2, is x2 to the power of 2 factorial, x3 over 3 factorial, and so on. You realize that the sine and cosine basically fills up, when they are added together, fills this thing up. There's a little bit of things missing, and what you realize is that when we plug in x equals to ix, so instead of plugging in x, we are plugging in I, where I is of course root of minus 1 into the expression, and then we remember that I squared is equals to minus 1, and then I cubed is minus I, and I4 equals to 1, and so on. And when we plug it in, what we will realize is this. You plug in e to the exponent of ix over here, and then now you substitute into this form so you have now, instead of x, you now put ix, you put now ix here, and you put ix square here, you put ix cube here, and so on. What you will realize is that when you also use the identity I squared equals to minus 1, I cube equals to minus I4 equals to 1, you get this expression. We then open up the brackets of ix squared to become minus x squared, because I squared becomes real number, and the positive sign becomes a negative. I cube becomes minus I, so we have minus I here. I4 becomes real again, so there's actually the I to the power of 4 becomes 1, so it is x4. So you realize that we have real terms in the even powers of x, and imaginary terms in the odd powers of x. When you collect them up together, so all this becomes the even terms, and all this becomes the odd term. And you realize that, hey, isn't this the cosine of x? And here, when you bring the I out, isn't this the sine of x? And this is how you derive the complex exponential form of ej theta of the Euler's formula ej theta to be cosine theta plus g sine theta using Taylor series expansion. For a detailed description, first, of course, you may want to review what is the Taylor series about. So I give you 2 lectures on Taylor series, and Taylor series is learned in calculus, so we're not going to repeat here. But the idea of Taylor series is that Taylor series expand a function about a base point x using this identity or this equation over here. Okay, a function f of x is approximated by this expression over here. Now, once you have understood what a Taylor series is, then I will suggest you read Brunton, where I use his results over here to show you why EIX is equals to cosine x plus I sine x. With that, thank you.